So welcome. This is the second part of the physics, which is part 2. It comprises question 12 to 17. We are going to take them one after the other. Make sure you stay tuned, watch deeply, understand the process. You can put your own thoughts, ideas into it. Question 12a is state the law of flotation. State the principles of flotation. 12a. Principle of flotation. Principle of flotation states that a floating body or object displaced its own weight in fluid. So weight in fluid on which it floats. A floating object displays its own weight in fluid on which it floats. It's also called the principles of buoyancy. That's what the law of flotation is referred to as the principle of buoyancy. Question 12b. So distinguish between a cone resting on its base and a cone resting on its apex. 12b. We have two cones, one resting on its base. So let's assume this is our floor. We have a cone like this. It's resting on the base, while we have another one like this resting on its apex. So this is the base. Right, this one is the apex. So how do we distinguish between them now? The cone resting on its base is an stable equilibrium. That's the one resting on its base. Why the cone resting on its apex is an unstable equilibrium, or example of an unstable equilibrium. So that is the difference between the cone resting on this base and the cone resting on its apex. So take notes. So that means the first one we displace and come back to the original position. Second one we displace but will not come back to exactly the original position. It will displace slightly from the original. Then while in neutral we occupy a new position altogether. That's a neutral equilibrium. So let's see question 12c. It says a force F is applied to move a body of mass m for a time t. If the initial velocity and the final velocities are u and v respectively, derive the expression for m in terms of the given parameters. So let's illustrate. I like illustrating my questions with diagram 12c. So let's say this is the object, has a mass m, a force is applied to it, which is F. So if the object we move, occupy is also the F, we now have our V. It will take time to move from here to here. Here is 0 and here is t. Okay, so we know from Newton's second law, let's state it. Because all these things count, I'll say from Newton's second law, we have F equals to ma, which is mass times acceleration. Let's call this equation 1. But we are deriving, you have to state all the datas. Then we have from first equation of motion, of first equation of motion, we have V is equals to U plus AT. Let's call this equation 2. So let's make if the subject formula from 2. So I will say from 2, I'm having AT is equals to V minus U. Therefore, my A is now what? V minus U over T. Let's call this one equation 3. So I will say put A from 3 into 2. Put A from 3 into equation 1. So remember equation 1 we say F equals to MA. So force equals to MA according to equation 1. What are we having? Implies that my F is now what? M into V minus U over T. But they are asking us to express M in terms of the other parameters. So what are we going to do from here? I will cross multiply. I'm going to have Ft is equals to M into V minus U. Therefore, my M now is simply Ft over V minus U. So this is the expression. Let's call this equation 4. So equation 4 now is the expression required from according to the question. So I hope it's clear. Let's go to question 12D. Question 12D said, or I can state their meaning. I can state their meaning for clarity. Where M is equals to mass, F equals to force, T is time, V is final velocity, and U equals to initial velocity. So take notes. So let's go to question 12D. Question 12D. It says a mass of 400 grams attached to a vertical spiral spring and set into motion. If its period is 2.0 seconds, calculate the frequency of vibration. So let's see question 12D. Like I said, I like illustrating my question with diagram. So the answer is the spiral spring contains a spring constant. Here's our K. At the end of the day, we have a mass of 0.4 kilograms. So the mass is given to us as 400 grams. We convert it to kilogram, which is 400 divided by 1000. So the mass will give us 0.4 kilogram. Okay, so it's the vertical oscillation, which is part of the practicals we did, is vertical oscillation of pendulum, of a spiral spring. Yes. So we are asked to find it. Then they give us the period T as 2.0 seconds. So let's see 12D romantic on 1. So romantic on 1 now we know that frequency is the reciprocal of the period. Okay, which is simply 1 over 2.0, I mean. 1 divided by 2 is what, 0.50 per seconds, or 0.50 hertz. Anyone can serve as the SI unit of frequency. 0.50 per seconds or 0.5 hertz. Then I've got 2, so you calculate the spring constant, which is our K here. So let's see how we calculate the spring constant. We've got 2. We know that period equals to 2 pi root m over k. So if I need the value of k, that means I will square both sides. If I square both sides, I'm going to have t squared equals to 2 pi root m over k all square. So the square should place rule. I'm going to have 4 pi square m over k. So I make k the square formula, which is spring constant. I'm going to have 4 pi square m over t square, which is, let's substitute our value now. So now implies my k is equals to 4 times, what's the value of pi? 3.14. 3.14 squared times 0.4, which is the mass, divided by 2 square, which is the period. So if I simplify this, my k will be what? 4 times. If I square 3.14 from my end here, I'm going to have 9.8596. So some people normally take it as approximately 10, but I like writing it in full. Okay, so you agree with me that this 4 can remove this 4, so my k becomes what? My k becomes 9.8596 times 0.4. So let me multiply from my end here. 9.8596 times 0.4, that will give me 3.944 Newton per meter. 3.944 Newton per meter. That is the solution to question 12A to D. So let's look at question 13. Let's look at question 13. Question 13 says 13A says why is claw hammer termed as a first class lever? We know a claw hammer. Let's look at question 13. A claw hammer is something like this. So you use here to remove nails from wood. This is a nail. So here will be fixed. Here is not the load. So your hands will be here. Your hand will be somewhere here. You're going to press it down with a force. That force is called the effort. So what is the point? The point is, let me erase this part. Let's see. So claw hammer is classified or regarded as a first class because the fulcrum is between the load and the effort. Between the load and the effort. So that is why that's why we classify a claw hammer as a first class lever. Okay, let's look at 13B. Roman figure 1. Say it is not advisable to sterilize clinical thermometer in boiling water. Explain. So if you've done that, if you have worked in the medical field, although it's in physics under measurement of heat and temperatures, that's why you see this particular question. 13B. Roman figure 1. So you should explain when a clinical thermometer, is sterilized on a boiling water, it causes an uneven expansion. It causes an uneven expansion of the thermometer. Cause an uneven expansion in the thermometer, which may cause crack on the thermometer and eventually leads to breakage. of the thermometer. So that is a simple explanation. Now, it says draw a well-labeled diagram of a hypsometer. Hypsometer in terms in use to determine the upper fixed point of an unmarked thermometer. So the upper fixed point is temperature of a boiling water. Don't forget that. So these two topics are under temperature and measurement. So 13b, Roman figure 2. So if I want to draw this diagram, you can also look it up. I will have my reactor stand. Here is the base. This is the reactor stand. Here is the base. Here we have a tripod. Here we have the wire gauge. So here we have a copper boiler. Here we have a copper boiler. The inside we have our thermometer. So we have our thermometer, something like this. So the thermometer is being held by the reactor stand. It's held by the reactor stand. Okay. So here there is water in this point. So just take here as your mark. So here becomes the unmarked thermometer. Unmarked thermometer. So here is also water is boiling, we have steam coming out. Then just here is my steam. Then here this one is the copper boiler. Copper boiler. Here is my wire gauge. Here we have there will be heat here, source of heat here. Here we have the tripod. Here we have the Bunsen burner. The Bunsen burner. Then here we have our reactor stand. So this is the diagram. So also check it out. So question 13c says sketch the charges distribution on an insulated circular conductor. So let's deal with that first. So you find this topic is also an one topic in the electric charge. That's where you also see this in new school physics. So let's see our 13c Roman figure 1. So we have something like this. Okay, here our electric field is 0. There we have uniform charges that's well distributed around the circular object. Now the positive charge distributed around it. A positive charge uniformly distributed around it. Okay. Here we have our insulated stand. Just sketching something like this. Our insulated stand. So let's see. So here is our insulated stand. So all the charges, you can see here, uniform charge distribution, which are the positive sign you are seeing there. Then here we have the mental conductor. Here is our mental conductor. This is our mental conductor. So this is for our circular circular conductor. That is the diagram of our circular conductor. So let's see. Now we've got 2. It said pear-shaped conductor. It's pear-shaped. You know pear? That pear avocado that you eat, it has a particular shape. So let's see. So 13C. And now we got 2. So the pear has something like this. How a pear look like. Okay, let me redraw it. It won't look horrible. Make sure you have a neat drawing. Depends. We sharpen it like this. Okay. So let's say something like this. So we also have charges distributed around it. Have charges distributed around it. Okay, so the inner part also we have charges also distributed. So from here to a certain point here, then here too, from this point we have charges distributed this way. Okay, something like this. So our E is also 0. Then we have our also have our insulated stand. Our insulated stand, something of this nature. So our insulated stand. So we're going to have, I'll label it. Here's our insulated stand, just like the first one. Then here we have the low charge density. Here is our low charge density. Then the upper part is our high charge density. High charge density. High charge density. So this is what we have as 13C. Okay, so let's look at 13D. 13D. And look at 13D. You see a piece of copper ball of mass 50 gram at 120 is placed into a copper calorimeter of mass 80 gram containing 100 gram of water. So let's illustrate this thing and see. 13D. So let's assume this is our copper calorimeter. You know, it's always lagged to prevent heat loss. So these are the lagging. It's always lagged to prevent heat loss. You say this copper calorimeter has a mass of what? Of 80 gram, and it contains water. It contains water. It contains water. So the mass of this water is 100 gram. Okay, and go back to the question. Okay, temperature of the mixture is 30. So what is the temperature of the water? They didn't give it to us. So let's take the temperature of the water as θ1. Like this is a copper ball of mass 50 grams. And the temperature is 120 degrees Celsius. So what happens if you hold this high temperature into this water? If you hold this high temperature into this water, meaning the temperature of this water will increase, and which is the temperature of the mixture now, and that value is 30 degrees Celsius. Okay, so if I hold the ball now into it, temperature of θ1 I have to increase. We now have it as 30 degrees Celsius. So what are we going to experience from here? What I'm going to experience when you put the 120 gram into this water, this mass will lose heat. Because like when you put a hot object in water, there will be heat loss now by the hot object. Who is gaining the heat? It will be gained by the water. And you also notice that with time, the body of this calorimeter will also gain heat. So the calorimeter will also gain heat. You will notice that the body will be hot with time. Okay, so what are we going to get from here? I will say heat loss by copper. Heat loss by the copper ball is equals to heat gain by water, not only water that gain that heat, plus, because the body of the water of the calorimeter will also hot, plus calorimeter. Okay, it's like when you put a hot object in a cup, the water become hot, the body of the container will also become hot. So what is heat lost by copper? It be mass of solid, basic capacity of solid, theta minus theta 2 is equals to mass of water, basic capacity of water, theta 2 minus theta 1, plus mass of calorimeter, specific capacity of calorimeter, theta 2 minus theta 1. That's what we are going to get. So the mass now of solid now, which is 50 grams, I'll convert it now to kilo, which is 0.05 kilogram. Then the mass of water, which is 100 grams, will become 0.1 kilogram. Then the mass of calorimeter, which is 80 grams, will become 0.08 kilogram. Okay, so with this now I can fix it now to find, we are looking for which temperature. They give us the temperature of the mixture. We're looking at the temperature of the water now, which is about theta 1. Okay, so I'm going to have a substitute. I'm going to have into this formula now. I'm going to have 0.05 times 400 with specific capacity of copper calorimeter. Then theta is 120 minus 30 is equals to, if I factorize, I can factorize theta 2 minus theta 1 from this expression, from the right hand side. Let's do that. Let's say we have theta 2 minus theta 1 as a common factor. Mass of water is what? 0.1. Specific capacity of water 4200 plus mass of calorimeter 0.08 times 400, which is the copper calorimeter. Also have the same, it has the same material as the ball, so you have the same specific heat capacity. So if I multiply from here, I'm going to have 0.04 times 400. That will give us, or let me just subtract 0.05 times 400 times 90, which is 120 minus 30. I'm having theta 2 minus theta 1 into, that will give us 420, which is 0.1 times 1200. That's 0.08 times 400. That will give us 32. So if I multiply my left hand side, that will give me 1800. If I multiply everything here, I'm having 1800 is equals to, if I add 420 plus 30, that will give me 452 into theta 1 minus theta 2. So let's make theta 1 minus theta 2 the subject formula. Theta 2 minus theta 1 now will be 1800 divide 452. What are we having? That will give us 3.98, which is approximately 4. So we are looking, what is theta 2 now? Is 30 minus theta 1 is equals to 4. Therefore, theta 1 will simply be what? 30 minus 4, which is 26 degrees Celsius. That's not the mass of the water. It's 26 degrees Celsius. Okay? So let's look at that is question 13D. Okay, let's go to question 14. Let's look at question 14. Look at question 14. For question A, say what is a wavefront? 14B says state the types of beam produced by searchlights and bulb. Let's take the first one first. What is a wavefront? This is question under waves and the light, reflection of light. So we have 14A. So wavefront is an imaginary surface, is an imaginary surface or line connecting all points of a nearby wave that are vibrating in the same phase, So that is the definition of a wavefront according to question 14A. 14B says state the types of beam of light produced by searchlight. So we are going to go to 14B, numeral 1. That's what we have, Roman figure 1, then we have numeral 1 and 2. 14B, Roman figure 1. So numeral 1, searchlight being produced by a searchlight is parallel beam of light. Is parallel beam of light. Then numeral 2, bulb. The bulb is a diverging beam of light. Diverging beam of light. So let's look at 14B, Roman figure 2. 14B, Roman figure 2. It said distinguish between regular and diffuse reflection. So it came out in the practicals, regular and diffuse reflection. So let's look at that. 14B, Roman figure 2. So regular reflection is a type of reflection. It's a type of reflection in which beam of light hits a smooth surface, and reflect or bounce in a parallel beam of light, in a parallel beam of light. Okay, so you can illustrate it with a diagram. So if light strikes, they will reflect in a very distinct manner. Okay, then why diffuse reflection is when a beam of light hits a rough surface. This time around it's not smooth. A rough surface and reflects or bounce in irregular direction, in an irregular, or another word, or scattered direction, So you can see illustrate it with a diagram if you want. Then that is question 14b. Let's go to 14c. It says an air column in a closed pipe of length this is set into vibration to set out to generate a wave at each fundamental frequency. So sketch the diagram. So let's look at 14c. We are dealing with a closed pipe here. So this is under closed and open pipe with vibration of sounds. So for a closed pipe, you are going to have something like this. And the length of this pipe, according to the question, is 50 centimeter. Okay, so that is the diagram for it. That is 14C, Roman figure 1. So the length of the pipe is 50 cm. So let's look at 14C, Roman figure 2. So calculate its wavelength and the frequency of the first overtune. So 14C, Roman figure 2. Now for a closed pipe, we have 1/4 of a vibration, which is the length now is 1/4 lambda. Okay, it's 1/4 lambda, and they gave us the length as what, 50 cm, which is something now 0.5 meters. So always convert from centimeter to meter. Physics does not recognize cm. The only language they recognize is meter. So let's substitute now to get the wavelength. I'm going to have 0.5 here equals to 1/4 lambda. Therefore my lambda is simply what, 4 times 0.5. That will give us 2 meters. That's the value of the wavelength now, or the lambda. Then once we go to, they are asking us the frequency of the first overtone. This is fundamental. So let's get our fundamental frequency. Okay, the first vibration is the fundamental. We know that V is equal to what? F lambda. Okay, V equals to F lambda. I want to establish a relationship, so follow up. Let's establish a relationship. So follow up with it. So what is my lambda? My lambda is 4L. So V now is now F times 4L. So my F now implies what? FO, which is the fundamental, is V/4L. Please take notes. V/4L. So I'm going to have my FO, which is the fundamental now, is 340/4L is 2. That is now 170 hertz. These are now the fundamental frequency. But they are asking us to calculate the frequency of the first overtune. For a first overtune, the pipe will now look this way. There will be a certain vibration. The pipe will look this way now, like this. This is for first overtune. So don't forget the whole of this length. Here is our L. So here is not here, from here to here is lambda/2, while from here to here is lambda/4. So what is the point? The length now is simply what? Lambda/4 plus lambda/2. The length now will give us, so my SCM is 4. Here's lambda plus 2 lambda. The L now is now what? 3 lambda/4. That is now the value of L for the first overtune. But don't forget what we stated earlier about equation 1. Okay, so let's draw the relationship. Let's draw the relationship. Where's now my lambda? My lambda will give me 4L divided by 3. So from here now, our lambda give us 4L over 3. So let's take this one as equation 2. I just trying to show you see how it is done. So we know that FO is V over 4 lambda over 4L. Yes, V over 4L. Okay, it's V over 4L, and 4L is our. So let's make. So from here now, I'm going to have FO is equals to V we know is F lambda, right? So if V is F lambda, so my lambda now, my V here now is now F times our lambda, which is 4L over 3. So let's substitute this V now in place of this V. So what are we having? I'm going to have FO is equals to 4FL divided by 3 over 4L. So 4L will cancel 4L. We're having what? F over 3. So the frequency of the first over 2 now is 3, the fundamental frequency, which is simply 3 times, what's our fundamental frequency is 170. 3 times 170. So the frequency of the first over 2 will give us 3 times 170, that will give us 510 Hz. So this is just the proving. You can just write F1 is now 3FO. So I've gotten your FO. This is just the proving to tell you how it was achieved. Just multiply it by 3 times FO. Which is 3 times 170. You're going to have 510 as that answer. That is solution to question 14C, Roman figure 2. So let's look at question 15. Question 15 say, what's the electric current? 15A, Roman figure 1. Electric current is the flow of an electron through a conductor. The flow of electron through a conductor. So it is measured. It is just to garnish it. Measure with ammeter. Ammeter, and each SI unit is ampere. We just to garnish the process. SI unit is what? Is ampere. So let's look at 15 Roman figure 2. It says take two factors affecting electrical resistance of a conductor. So 15A Roman figure 2. We know a resistance in resistivity is resistivity of the wire length over what? Over area. So what are the factors now? 1, length of wire. 2, cross-sectional area of the wire. 3, we have the resistivity of the wire. So you can state then number 4, you can pick any two. Number 4, temperature is also the factor. Temperature. So these are the factors that affect the resistance of a wire. So let's see question 15B. It says draw in the magnetic field round 2 bar magnets with their south poles facing each other. With their south poles, that's 15B Roman figure 1. 15B Roman figure 1. So if their south poles facing each other, this is what we have. Here is north south. Then this is the other bar magnet. Here will be south north. So we have, that means here is a neutral point. Then you draw the magnetic line of force. So we're going to have something like this. So the flow is going this way, or you also have it this way. So the flow is also going this way. So with the flow coming like this. So the same way I'm going to draw for the other side. We have, yes, we have charges going this way and this way. This is coming in, coming in, coming in, coming in. So we do the same for the other. Here I'm going to have, make sure you space them. It's just a rough work. It shouldn't be touching each other. Then here we have the other one will go this way. So the flow like this. This one is coming this way. Then we have this. They are going in, going in. So this is the first case, but make sure you space it for clarity. So this point here is our neutral point. Our neutral point. So make sure your diagram is well spaced. Then the second said around a solenoid. So 15B Roman figure 2. So around it, you know what a solenoid is? I look that out. Around the solenoid we have something like this. This is how a solenoid is, with okay. Then we have our magnetic field, I mean. So we have the first point, say from here to here, here to the second point, then here I have another point here, let's say from here to here also, and the other one will be in this manner also. So we also have our feed in this direction, our feed in this direction. Okay, so you must indicate the direction. Okay, this is so this is also going this way. So this is around a solenoid. So that is that. Then 15C, he said the circuit diagram is shown above. So look at the question. These two are connected in parallel. It say combine, calculate the combined resistance of the parallel resistor. Okay, so we have 2 and 5 are connected in parallel. So 1 over R in parallel will be 1 over R2 plus 1 over R5. Basically 1 over 2 plus 1 over 5. The SM is 10. I'm having 5 plus 2, which is 7 over 10. So my resistance in parallel will simply be what? 10 over 7 ohms. So what about the combined resistance? Combined resistance now, which is they are not combined. These two now will be combined in series with this. So I'm going to have total resistance now, RT will be my R4 plus R in parallel. I'm having 4 plus 10 over 7, which is 28 plus 10 over 7. Yes, over 1. If I take SCM. So my RT will be 38/7, which is if I divide, I'm going to have 5.429 ohms. That is now the total resistance. So we are now asking us, question 2 now, they're asking us to calculate the current. Asking us to calculate the current in the circuit. So they gave us our EMF and our internal resistance. So we know, remember we got 2, we know that I is the EMF, total resistance plus the internal resistance. So my E now will be what? What is the EMF given to us? Our EMF is 2. Total resistance we calculated is 5.429 plus internal resistance 0.5, which is 2/5.9285. If I should divide by that, I'm going to have 0.337 ampere. So this is now the value of the current according to question 15. So hold on for 16 and 17. So if you have not subscribed, please do so, like and share. As we're going to post others like technical drawing, further mathematics, chemistry will be posted. So stay tuned to this channel if you must get other exciting videos. Stay tuned to it. Like, share and comment. Like, share and comment and subscribe to the channel, and make sure you stay tuned to the other areas. Make sure you stay tuned. So let's go to question 16 and ultimately question 17. Let's see how it goes. Question 16 and 17. So let's look at question 16 here. It says we should define viscosity. So we should define viscosity. So what is viscosity? 16A. 16A. So viscosity is the resistance offered by a liquid or fluid to flow. Is the resistance offered by a liquid or fluid to flow. That's what we call viscosity. Let's look at 16b. Say make sketch and label the cooling curve of a pure crystalline substance. So how do we sketch the cooling curve of a pure crystalline substance? 16b. So we're going to have something like this. This is time in seconds, but this is temperature in degrees Celsius. So it's cooling, meaning it's coming from the higher temperature to a point like this, then down. So here is cooling. Here is the cooling phase. Let me label. Here is A, B, C, and D. So AB is the cooling liquid. Then BC, after cooling, when it's steam cool, what next will be freezing. It becomes water. Freezing. Then here is the Then C to D is solid. Cooling of solid. Let me say cooling of solid. That is C to D. Then at this point, each of them will produce a certain time. Here is T1. Here is T2. So from B to C take place at constant temperature. B to C take place as constant temperature. Then here, let's call here Tm, which is our melting slash freezing temperature. Okay, so this is the diagram for 16b. 16c said a certain radioactive salt has a half-life of 4 days. If this in solution contains 50 grams of the salt on the certain day, tabulate the mass of the salt that will remain after 4, 8, 12, and 16 days. Then use the table to plot. Use the table to plot a mass against time. That's 16c. 16c. We know that the mass over the original mass is 1 over 2 T over half-life. So the mass that will remain now is the original mass into 1 over 2 the time over the half-life. So for our original mass is 15 grams. So what happens if it decays for 4 days and the half-life is 4 also? Our half-life is 4 days. So my N1 will now be 15 into 1 over 2 4 over 4, which is 15 times 1 over 2. That will give us 7.5 grams. Then what's the next day is 8. So I'm having N now, which is my N2 is 15 into 1 over 2 8 over the half-life, which is 15 into 1 over 2 raised to power 2. It's simply 15 divided by 4. So my N2 will be 15 divided by 4 should give us 3 points from my end here, 3.75 grams. Then after 8 days is 12 days, so my N3 is now 15 into 1 over 2 12 over 4, which is 15 into 1 over 2 raised to power 3, simply 15 over 8. So my N3 will give us 15 divided by 8 from my end here is giving me 1.875 grams. Next, with our N4, I'm going to have 15 into 1 over 2 16 divided by 4, which is 15 into 1 over 2 raised to power 4. It's simply 15 over 16. Our N4 will now be, if I divide from my end, 0.9375 grams. So from here now I can now do the tabulation. I should tabulate. We have the mass and the time. So the first mass, the time is 0. Then for the 7.5, which is second, is 4 days. The time in days, while this one is in grams. So don't forget the units. Then for 3.75, I'm having 8 days. For 1.875, I'm having 12 days. From 0.9375, I'm having 16 days. So this is the table. Not only that, he said you should plot mass against time. So I'm going to draw on the graph. Here's now the time in days. Here is the mass in gram. starting from 0. So you can use 2 cm to 2 units. We're going to have 2, 4, 6, 8, 10, 12, 14, and what, 16. Yeah, I can use 2 cm to 4 grams, 4, 8, 12, 16, and 20. So you can stop it here. So when it is 0, is 15. 15 before between 14 and 16. We mark here. Then when it is 2, when it is 4, when the mass is 4 grams, we are having 7.5. So if you count, 7.5 to here is 8, very close to 8. That should be our 7.5. So you should know how to count it. I've taught that in chemistry practicals. Then for 8 days, 3.75. This abundance will be above 2, close to 4. Then for 16 days, 0.9375, very close to 1. 1 is between 1 and 2, very close to 1. So at the end of the day, you're going to have, use a broom or anything to achieve a smooth curve such as this. Now let's see. This is state the mass of the salt that will remain after 15 days. The mass of the salt that will remain after 15 days. So after 15 days, what are we going to have? 15 days should fall between somewhere here. 15 should close to 16. Increase it to here. Whatever you have here, you should be able to figure that out tomorrow. That's the mass of the salt. With that, we have taken care of question 16. So let's look at question 17. It's the state use of continuity tester. Continuity tester, these are electrical devices. Continuity tester, let's state the use of a continuity. So I can state 2 or 3. Number 17A. 1, to check wire and cable integrity, whether they are still okay or not. Integrity. Then 2, to verify fuse and circuit breaker. I'll write a letter, so pick anyone. Then to detect short circuits. To detect short circuits. Anyone can serve. Then let's look at 17B. It says mention 2 instances of a use of a simple machine. 17B. Instances of a use of a simple machine. Number 1. So number 1, we have the screw jack to lift. What you use for to lift vehicles up for repair. 2, we have the inclined plane to roll objects or load, up the plane, to roll objects or load up the plane. 3. Then we also have the wheel and axle. The wheel and axle is applicable. You can use it to fetch water from the well without stretching yourself. Then we have the lever, which instances where we use lever, where 2 children are playing. The 2 children balancing a seesaw. A seesaw is an example of a lever. So any of them can serve as question 17B. Then question 17C says state the advantage of using prism over mirror in a periscope. Periscope are largely applied in submarine. Number 1, prism is hard and not subjected to stress. Prisms are thick, or let me say hard, thick solid, arctic solid block that do not distort under stress, while mirror distorts under stress. Then 2, as a prism produce brighter images than mirror. So let's leave it as such. You can figure out another. Say the advantage just one, so you can pick anyone. Then 17D, you say the table 2.1 shows the summary cells and the components complete the table. So 17D, so to complete the table, we have something of this nature. We have the positive terminal, negative terminal, and the electrolyte. This is the cell. We have 2. We have the link cliche cell. Then we have the NECO ion. Okay, so the positive terminal, let me say positive T. The T for terminal, negative T. Here is now the electrolytes. So the positive terminal for link cliche made up of carbon rod, while the negative made up of zinc rod. The electrolyte here is ammonium chloride, while the NECO ion, here we have the NECO plates. The negative terminal, we have the ion plates, and the electrolyte is potassium hydroxide. So that is the table. Then number 17E, say a slide projector is used to produce an image on a square slide of side 10 cm. Then onto a screen placed 100 cm from the lens. So that is our image that will be formed. 100 cm from the lens. So if the image square is this, that is our image height. Calculate the magnification. So we have a 17E. So let's state out our given data. It gave us the object height as 10 cm. Then the image height as 110 cm. We have the image as 100 cm. So the magnification is image height over object height, which is 110 divided by 10, that is 11. So here is cm, here is cm. Both of them will remove themselves. Then now we got 2. So we should calculate. Let me calculate the object distance. We know that magnification equals to image over object. It implies that the object now is now V over M. What is V? So 100 divided by 11. So my U now will simply be 9.09 centimeter if I should divide it. So this is the solution to the entire physics question. So stay tuned for objective. If you have not liked, subscribe, please do so while you have the time, and stay tuned to the channel for further maths, chemistry and technical drawing. See you in the objective section.